This meeting is being recorded.
In section 10.3, we're going to look at a specific radical mechanism involving the chlorination of methane. So in the first step here, the first phase of this reaction, when we chlorinate methane, this will be our initiation step. So this is where chlorine radicals will be created. And we see down below this Cl2 indicated here will have homolytic bond cleavage. In this case, we're using light to cleave that bond. So that's how the energy is being added to break that bond. So we're going to see each of these distinct stages. So methane, again, right, will be our reagent, and we're going to chlorinate this. So in our initiation step, so far we're here. We've added light, we've created 2 chlorine radicals. So let's see what happens in our next step, in our next steps, possibly, when we have propagation. These will usually be multiple steps, and they are told here to be self-sustaining. So what that means is that in step 1 here, we're going to do this hydrogen abstraction. So that's the pattern that you should see. So this chlorine radical pairs up with this hydrogen here, and we're going to form this HCl here. At the same time, we are creating this radical here. And for whatever reason, it looks like my other hydrogen didn't transfer over in these images. So now we have the self-sustaining part. We'll see that this radical is created here, and then in a subsequent step, we'll see this utilized. So either this radical here or this radical here, we can see being used in other steps. So just like the hydrogen abstraction, we have a radical, breaks a double bond here by grabbing one of the electrons, and then we have added a chlorine to our methane here so far. So let's look at what happens after the propagation steps. So we have radicals that collide here. So 2 chlorine radicals can couple and we destroy, right? We end each of those radicals and form a diatomic molecule. We could have coupling again. So the chlorination of methane specifically would involve this type of coupling reaction here. So we have a methyl radical and a chlorine radical, but we destroy these radicals through this coupling reaction, and then we have no longer those radicals existing to continue to propagate that reaction. Our last example of termination is when we end up with ethane as our product when 2 methyl radicals combine in a coupling step, in a coupling reaction. So I had mentioned that it's a self-sustaining reaction, and let's look at this in this type of equation, this summary, and what happens in our net reaction here. So during the propagation steps, we were told that they were self-sustaining, and another way of saying that is that they are a chain reaction. So in our hydrogen abstraction, in that first step listed, we have our methane rather, we have chlorine here. So we have a chlorine radical that grabs the hydrogen, forms HCl, which is our product listed here. And then we have this methyl radical. So during the halogen abstraction, we see the methyl radical canceled out. Also, the halogen abstraction step produces that chloride radical that is utilized in this hydrogen abstraction. So that's why we say this is self-sustaining. So what's produced in the second step here, the product of a later step, is then served as a reactant in an earlier step. So this is how this is a chain reaction or self-sustaining when we talk about the propagation of radical reaction mechanisms. So polychlorination, right? You might have been asking yourself, are we just going to add one methyl group to our, one chloro group to our methyl substituent? Well, So if we did that, we would have one equivalent, right? One chlorine added per methane. But methyl chloride is more reactive towards radical halogenation than methane is, right? So since this is more reactive, it's very hard to prevent. So if we did not have excess and we only wanted monochlorination, we would need a lot more methane than the Cl2 species to only have monochlorination happen, or else we could end up with theoretically up to carbon tetrachloride here. So all four of those hydrogens could be replaced with chlorides. So again, we can take a look here of some different radical initiators. So we saw dihalide. So these will be those X's, right? So we could have anything from chlorine or bromine to produce two radicals here. And over here is the amount of energy that will be needed to cleave that bond homolytically to create those radicals. With an alkyl peroxide we see here, we could create two of these RO radicals, and notice that the energy is significantly less than a dihalide. And if we have this last species here, these acyl peroxide, so we would create two radicals of these two acyl groups. That has the lowest type of bond association energy associated with it. So this will be the most reactive, and it's also effective at temperatures up to 80 degrees Celsius. So we don't need to increase the temperature that drastically, rather. So I should rather say low enough temperatures can be maintained in these reactions. So acyl peroxides are a good choice if you want a lower temperature than is needed to break bonds at those higher temperatures of dihalides, etc. So these radical initiators start reactions, but we also have things that are called radical inhibitors. So these would react with radicals that are created to stop that propagation from occurring. So to prevent the chain reaction. So if you do not want a radical mechanism to cause a propagation and then chain reaction to happen, you can use inhibitors such as hydroquinone, which could react with two radicals, or this oxygen diradical could also react with a radical over here or a radical over there. So whether you want to continue your reaction with propagation or inhibit it, you have choices if you use inhibitors. So let's take a look here. This last slide shows us that mechanism of action. So hydroquinone, this species here that was mentioned that could be used as an inhibitor, encounters a radical here. And when that itself becomes a radical due to hydrogen abstraction, right? So this electron from the bond and this electron form this RH species. So that radical that was a harmful radical, or a radical that would continue propagation, will be prevented from reacting any further. And this radical that's created is resonance stabilized, so it will be much less reactive overall. And then we see something similar down here in this second step here, and this benzoquinone resonance structure. So we'll continue with section 10.5 in the next video.